Good evening, everyone, and welcome to the 2020 Virtual Grand Canyon Star Party. I'm Ranger Raider Lane, the National Park Service coordinator for the event. For 30 years running, Grand Canyon has been celebrating our pristine night skies through this annual event we call the Grand Canyon Star Party. Ordinarily, we invite hundreds of astronomers and thousands upon thousands of visitors to the park to enjoy 8 nights of some of the darkest night skies in the United States. Yet each evening is typically kicked off with a special guest speaker in our theater. That's followed by telescope viewing, constellation tours, night sky photography workshops, and much, much more. Next year's Grand Canyon Star Party is June 5th through the 12th, 2021. So mark your calendars and cross your fingers that we will be able to celebrate that on site here at the park next year. This year, we want to bring you a taste of Grand Canyon Star Party in the virtual realm. We want to try to mirror how a night at Grand Canyon Star Party might unfold on site. So we're lucky to start each evening with one of our special guest speakers who are all willing to share their talks with us online this year. And we're excited to bring you some of the wonders of the summer sky into your homes with our virtual telescope viewing sessions that will premiere right after this program. Before we introduce our special guest this evening, I have just a couple of entities the National Park Service would like to thank for their support in this event. First, I really want to thank Grand Canyon Conservancy. Now, they're the park's official nonprofit partner. Their current priorities in the park are all amazing. I mean, that includes trail restoration, the Desert View Intertribal Heritage Site. They fund research and education in the park. And of course, one of their top priorities is night sky preservation. So through the generous support of Grand Canyon Conservancy and all their supporters, Grand Canyon National Park was able to inventory over 5,000 lights in the park over the last few years to be night sky, inventory over 5,000 lights in the park and retrofit over 1,500 of those lights to be night sky friendly. Okay, and this allowed us in 2019 to become certified as an international dark sky park, which undoubtedly makes us one of the largest, most complex, highly visited international dark sky parks in the world. That very same year, the park was awarded the distinction of International Dark Sky Place of the Year by the International Dark Sky Association. Now, they're the nonprofit entity that certifies parks and communities as international dark sky places, among a whole host of other things that they do. In fact, the International Dark Sky Association's mission is to preserve and protect the nighttime environment and our heritage of dark skies through environmentally responsible outdoor lighting. We thank the International Dark Sky Association and their tremendous staff, and we hope they keep up the great work. Finally, Grand Canyon's International Dark Sky Place of the Year could not have been achieved without the dedication, the passion, and the expertise of the Tucson Amateur Astronomy Association. They're our essential partner for putting on the Grand Canyon Star Party each year. Now, in our virtual telescope viewing sessions following this presentation, please thank the astronomers in the chat room. They're going to be populating the chat room, answering questions for you all, and they do this out of pure love of the night skies on a volunteer basis. The National Park Service is really proud to work with them in this endeavor. And with that, I want to introduce tonight's special guest speaker. Tonight, we are really lucky to have Professor Vishnu Reddy with us. Vishnu Reddy is an associate professor of planetary sciences at the Lunar and Planetary Laboratory at the University of Arizona in Tucson. Prior to serving as a faculty member at the U of A, he was a research scientist at the Planetary Science Institute in Tucson, Arizona from 2012 to 2016. Professor Reddy is a member of NASA's Dawn mission, working with the framing camera team at the Max Planck Institute for Solar System Research in Germany. Professor Reddy is a co-investigator on NASA's Near-Earth Object camera mission to discover 90% of near-Earth objects larger than 140 meters. In addition to his work with NASA, Professor Reddy is part of the Space Situational Awareness Program at the University of Arizona, where he has developed a network of small optical sensors to characterize orbital debris and active resident space objects for the United States Air Force Research Laboratory. Tonight, Professor Reddy will present Planetary Defense, Surveying the Sky for Killer Asteroids. Professor Reddy, thanks so much for joining us tonight.
Thank you, Lane. It's a great pleasure to be here and share the story I have to tell today. So let me go ahead and share my screen. All right. So today I'm going to talk about something I'm very much involved in, which is planetary defense. So 50% of my work works with planetary defense, and the other half I do space surveillance for the Air Force. So we've all seen the Hollywood version of what asteroid threats are like. So here, this is a famous movie, Armageddon, and you can see them trying to figure out what would be the impact from a large asteroid. Luckily, there are no asteroids as large as Texas that pose a threat to the Earth. If you go out in the night sky around this time, in the evening sky, you would see, the constellation Gemini. You could see the two stars Castor and Pollux, and just below it, you would see the planet Mercury. And if you have a really good telescope, you could actually image Mercury with its telescope and resolve some features, surface features on Mercury. So I've shown some amateur images of Mercury. It shows its phases just like our moon because it's an inner planet. Mercury and Venus both do that. And if you're early riser, if you get up around 4 in the morning, just before twilight, you would see planets Saturn and Jupiter very clearly visible, looking south to southwest in the sky. You can also see the moon, and with a decent sized telescope, you could see the bands on Jupiter, the Great Red Spot, and of course the magnificent Saturn rings, and close to to the left of Saturn, I think. You would also see the planet Mars. So here's a little image of Mars taken with a small amateur telescope. And the interesting thing is that these are what we call as the major planets. Planets we can relate to, planets that have been known since historical times. But there are thousands of small worlds, millions in fact, that we don't see with the naked eye, that are also going around the sun, just like the big planets. And these are what we call as the asteroid belt. So here I show a view of our solar system from the top. The sun is in the middle. The first little red circle is the orbit of the planet Mercury. Then you have Venus, Earth, and then you have Mars. And between Mars and the outer circle, which is the orbit of Jupiter, you see the swarm of what looks like bees, little dots. These are all the known asteroids that have been discovered so far. There are a little under 1 million of them that we found. And the red dots are different type of asteroids. They're called as Hildas and Cybele, but they're also in the main asteroid belt. That's what we see from here. And occasionally, due to the gravitational perturbation of Jupiter, these asteroids get pushed into the inner solar system, and they become what we call as the near-Earth asteroids or near-Earth objects. So we have about 22,000 of them. And those are the ones you hear about in the news, that they make a close approach to the Earth, or they fly between the Earth and the moon, or sometimes people, propose them as being hazardous to the Earth. So if you take a closer look, these red dots you see are all the near-Earth asteroids. So near-Earth objects, or NEOs, include near-Earth asteroids and near-Earth comets, but 99% of them are asteroids. Only 1% of them are comets. Of these 22,000 near-Earth objects that we have, about 2,000 of them are potentially hazardous. So what does it mean? It means that an asteroid is large enough and comes close enough to the Earth that could potentially cause damage. If you have a large asteroid that doesn't come close to the Earth, it is not potentially hazardous. If you have a small asteroid that comes really close to the Earth, it is not potentially hazardous simply because it might not, make it down to the surface. The atmosphere might filter it out. Through a telescope, asteroids look like points of light. So here there's an image of a star field. A few of them are stars, but one of these dots is actually an asteroid. So unless they hold up a sign saying, "I'm an asteroid," you would not be able to identify it. So how do astronomers go about finding asteroids? We use telescopes, obviously. So here's an image of the Catalina Sky Survey, which is actually just on the east side of Tucson, Tucson, and it's actually situated on Mount Lemmon. And this telescope survey is one of the two most prolific asteroid surveys that are currently operational. The other one being in Hawaii. And Catalina Sky Survey has found about 50% of all those near-Earth objects. So half of those 22,000 objects have been found by Catalina Sky Survey, and another telescope on Kitt Peak, which is on west side of Tucson. So here's a look at the Space Watch telescope, which is on Kitt Peak on the west side of Tucson. Both these telescopes have found about 50% of all the near-Earth objects that we know so far. So what is the technique that astronomers use to find an asteroid? So it is called astrometry. It sounds complicated, but it's not. What you do is you take a picture of the night sky, and then you wait. And then you take another picture, say 10 minutes after that. So, and then another picture after 10 minutes, and another picture of 10 minutes. So you have 40 minutes worth of images that you've taken 10 minutes apart. And what you do is you create an animation. So here you can see all the images have been stacked and aligned to the star position. The asteroid, you can see here with my mouse, I'm trying to show you, is actually slowly moving to the top right. And what is happening here is that stars which are around the asteroid are actually beyond our solar system. So they're really far away. So their motion is not apparent within the 40 minutes it took to get this animation going. But the asteroid is actually closer to us. In other words, it's in the solar system, and it's actually moving faster than the stars. So that's why you see the asteroid moving across the star field. So that's how astronomers find asteroids when they can't identify them through a telescope. So even amateur astronomers can actually find asteroids. Several thousand of them have been found by amateur astronomers, over the course of history. So the technique we talked about was astrometry. So what we try and do is we try and measure the positions of the stars that are in the background. Just like on the Earth, we have latitude and longitude. We have the same thing in the sky. So the latitude and longitude in the sky are called right ascension and declination. So on the top left, you see a globe and you see the location of the equator. The latitudes go, north-south. The longitudes go east-west. And the same way, on the right side, you have what you call as the celestial sphere. And right ascension is similar to the longitude on the Earth, and declination is similar to the latitude of the Earth. And every star in the sky has a latitude and longitude, or in other words, right ascension and declination information. So we know the position of the stars. So by knowing the position of the stars, we can calculate the position of the asteroid. And then as the asteroid moves from one position to the other, we can measure the rate of change of position with time, and which essentially tells us the orbit of the asteroid around the sun. So it's a very simple technique, but it's very elegant. So here's a software program we use to identify the target, just to give you an example. And so here's an asteroid. So this asteroid that we've just animated and shown here, the big black blob, is actually the largest asteroid in the asteroid belt. Remember a few slides ago, we saw the view of the solar system from the top with the swarm of bees, which I called the million asteroids that were going around the sun between Mars and Jupiter. This particular asteroid, asteroid Vesta, is the largest asteroid in the asteroid belt. So it is about 500 kilometers across. Now, we're going to play a little game. I'm going to let you guys take a look at these two images. One of these dots is actually an asteroid. If you're smart enough to figure out which one it is, in the time I'll give, you're pretty good at identifying patterns. So we've seen the left image, and the right image was taken a few minutes later, say 20 minutes later. So I'm going to show an animation now, and then you can find out if you're right or not. So the biggest object is the asteroid. So any guesses which one is this? Okay, so let's see. So this one is actually not an asteroid. It's actually a dwarf planet. It's called Ceres. So Ceres is the largest object in the main asteroid belt. Remember the distinction. The largest asteroid in the asteroid belt is asteroid Vesta, which we saw previously. The largest object in the asteroid belt is actually Ceres, which is actually a dwarf planet, similar to Pluto. So the dwarf planet Ceres is about twice as big as Vesta. It's about 1,000 kilometers across. And now we're going to make it a little bit more complicated, a lot more stars, right? So you can see how difficult the problem becomes. So if you can carefully look at it, here's the asteroid that is moving across the sky. So astronomers use computer programs to do the work that we're trying to do visually. At one point they did it visually, but soon they realized that it's better to do it using photographs and now with digital cameras. So a bit more complicated star field. Again, if you guys can pause the video and take a close look and take your bets as to which one is this asteroid, that'd be great. And it's really tricky even with the animation. It's right here. You can see the faint star moving, which is actually an asteroid. It's a dot. And the reason why these look like stars are they're really small. Like I said, the largest asteroid is about 500 kilometers across. And most of the asteroids are a few tens of kilometers, not very big at all. So comets, on the other hand, remember we talked about 1% of the near-Earth object population is actually near-Earth comets. Comets are easier to identify because they have a non-stellar appearance. In other words, they have some structure around it. So they have a little atmosphere that you can see. It's usually in the form of a coma, and they have also a tail. And of course, if you animate it, you can clearly see it. Similar to an asteroid. It's moving with relative to the stars. Some comets are really big and bright, so you can see a big comet here, and then when you animate it, you can see the star background moving and the comet is moving to the top right. So here's a tricky one. I'm going to show the animation. Anybody can guess what this object is? It's a very famous object, but you can take guesses within your house and see who gets it right. It's not an asteroid. It's actually Pluto. So it used to be the ninth planet. I think it's still the ninth planet, but they call it a dwarf planet now. So you can pick your type to describe it. So why should we care about these asteroids? So we have many problems in the world to deal with, but history tells us something very important. Of the 5 great mass extinction, the most recent of which happened 65 million years ago, when a 10-kilometer impactor, possibly a comet, hit off the coast of the Yucatan Peninsula in Mexico, and what created what is called as the Chicxulub crater. This basically led to the extinction of the dinosaur. It led to the rise of our own ancestors, the early mammals, and most of the objects, most of the animals that are on the surface of the Earth faced extinction. Anything in water, anything that depend on plant life. So only small mammals that could burrow themselves into the ground, kind of like little mice, they managed to survive. So here's the location of the impact site itself. It's an interesting story how they found this impact site. Originally, they were drilling for offshore oil, and that's how they came across interesting geological fragments from the impact site itself. So they're studying those samples, they were able to identify that there was an enormous event that shocked these rocks in such a way that could only have formed. And of course, when they mapped the surface, they found the actual impact crater itself. And you see debris from this impact site all over Mexico, in fact, all over the world. It's a KT impact layer. More closer to home, actually, closer to Grand Canyon, we have the Meteor Crater in Arizona. It's the only crater that is perfectly preserved within the continental United States. It was formed about 50,000 years ago. We had a 50-meter impactor, most likely made of iron, that hit the Colorado Plateau and formed this, impact crater. Recently, as a little over 100 years ago, we had the Tunguska event over Siberia. We're actually coming up on the June 30th, which is celebrated as the Asteroid Day. So the Tunguska event anniversary is the one that is celebrated as the worldwide Asteroid Day. So there's events associated with it. In this case, we had an airburst, so there was not actually a physical impact like the meteor crater, but there was of possibly a 60 to 190 meter object, and the shock wave flattened trees for thousands of square kilometers. So when people finally got to the location, as you know, 1908 was a politically charged year in Russia, which Siberia is part of. So it took a while for scientists to get to this location, and when they came there, they saw, trees being flattened for, hundreds, if not thousands, of square kilometers. And within our lifetime, we had the impact of Comet Shoemaker-Levy 9. So this happened in July 1994. We had a 2-kilometer comet, possibly got too close to the gravitational field of Jupiter, and it got broken apart into 21 fragments. And over the course of a week, each of these fragments impacted Jupiter. Now, mind you, unlike the Earth, what we see from the Earth is basically the gaseous atmosphere of Jupiter. So we don't see physical craters like we see on the meteor crater like we see on the Earth. So these poke marks that you see, the brown disturbances you see, are actually the debris that is being pushed up into the atmosphere by the comet's impacting the surface. And Shoemaker-Levy is an important event within our lifetime, not just for the scientific aspect of it, but also till that point, we did not take the impact threat due to asteroids very seriously. One of the impacts due to a fragment called fragment G created a fireball, the plume that you see, that was larger than the diameter of the Earth. In other words, if that fragment would have hit the Earth, we would have sterilized the whole planet. That would have been total, destruction of everything as we know on the surface of the Earth. So this gave everybody a pause, not just the scientists, but also the United States Congress. And they actually paid close attention to this problem since then. So after Shoemaker-Levy 9, the United States Congress authorized NASA to discover and catalog 90% of near-Earth objects larger than 1 kilometer within a 10-year time frame. So we'll see why they arrived at these numbers shortly. And because of this congressional authorization, there were several surveys that were funded. And this mission was largely accomplished around 2005, 2006. Remember, Shoemaker-Levy happened in 1994, and we had Congress take action right after that. And within 10 years, we were able to find 90% of the near-Earth objects larger than 1 kilometer. So here's a picture of a telescope that is in New Mexico, operated by the United States Air Force, by MIT's Lincoln Lab for the Air Force. It's called the Linear Telescope. A lot of asteroids and comets during that time period were found with telescopes like this. So why did they pick 1 kilometer? So here's a little bit of an eye chart, and I'm going to walk you guys through this. On the bottom axis, you see asteroid size in kilometers. So apology for those using miles. Astronomers primarily deal with kilometers in this case. So on the rightmost side is 20 kilometers. On the leftmost side is about 10 meters. You can see different impactors marked there. So when we looked at the dinosaur killer KT impactor, that's about 10 kilometers. We talked about it a few slides ago. Then as you move to the left, you have the 1908 Tunguska event. It's about somewhere in the 60 meter range, 60 to 190, but we're going to pick 60 for now, the smaller size. And then as you move to the left, you have the 2003 Chelyabinsk event. That's about 20 meters across. And on the left axis, you see number of near-Earth asteroids. In other words, as you go along the red curve, the number of asteroids increases at that size range. The simple message from the red line you take is that there are not many asteroids that are as big as the dinosaur killers out there. In fact, there are very few to none. Okay, most of the asteroids that are out there are very small ones. You can see the numbers on the top left side. As you get to tiny objects, you're approaching tens, if not hundreds of them. That's what you're looking at. So the threat from small asteroids is more, although the damage they could cause is relatively less. As you can see, Chelyabinsk, what it had cost. The other thing you see is completion plot, the blue curve that you see. How many asteroids we have found so far in a certain size range, and As you get to the larger size, you see these up and down dips simply because the number is very small. So we don't have as many objects. So that's just due to statistics. The most important thing that as members of the public you would like is the text in purple, impact devastation, that's on the top. So we noted before, Chelyabinsk was a bad day for people who were close to the windows because they had a lot of cuts from breaking glass, but a good day for window replacement business. So impact devastation is almost none at that size range. Well, when you get to the Tunguska size range, you're looking at destruction of cities, a city like Phoenix or Tucson or any other large city. And then if you go to larger size, you have regional damage. And then even bigger, so now we're approaching that 1 kilometer. Now, as you can see, Congress picked something with the help of scientists, something that would devastate a continent. So they wanted to quickly find, are there asteroids out there that could destroy a whole continent? Because that could cause a lot of damage. So that's where the 1 kilometer comes. And of course, the global destruction, as we know from the dinosaur killers, those are larger than 1.6 kilometers and up to beyond. And the good news is there are no asteroids as big as Texas, like we saw in the movie Armageddon. So most of them are much smaller. So we can rest in peace. So how are we reaching the goal? So here you can see in this plot, you have time on the bottom axis. It's 1980 to 2020. And then you have number of objects discovered on the left axis. So what you see here is that the red curve in the bottom, that is the 1 kilometer asteroids. And you can see that it's plateauing. And what the plateauing says is that we're finding the same asteroids we found before again and again. And you might ask, how do astronomers know if they all look like dots? How do they know that they're finding the same thing? Because remember, we're trying to get their orbits. Asteroids usually don't stray, from their orbits within our lifetimes, for a few hundred years. They're pretty good at staying within their orbits, unless they make a very close flyby of a large planet. So what we start to see is that, how do you know you made 90% goal? You usually start seeing the same asteroids over and over again. So that means it's like, catching fish. You catch and release enough fish. If you're finding the same fish again and again, that, you probably sampled a lot of fish in the pond, similar to that. So the United States Congress came back and said, NASA, you did a great job. Now we want you to go back and discover 90% of the NEOs larger than 140 meters within 15 years. And I forgot to mention why they picked 90%, not 100%. When you do the cost-benefit analysis, it's a lot easier to find 90% than 100%. You will spend a lot more for the last 10%. And eventually, people will find the 10% beyond the 10 years anyway. So you don't have to worry about it. Finding most of them is the most important thing from a risk point of view. And the budget went up from $2 million to $4 million to $20 million to $40 to $50 million. And now we're at about $150 million. But we soon realized that this is a bigger problem. Here's a telescope that is doing a fantastic job of trying to find these 140-meter objects. It's the Catalina Sky Survey, just east of Tucson. Go back to our plot. Why did they pick 140 meters? As you can see, this can cause regional damage. So it can take out, say, the Southwest United States if an object that size hits, or a small country in Europe. So that's the reason why they picked 140 meters. So how many 140 meters objects are there? So scientists estimate there are about 25,000 objects larger than 140 meters. Okay, and we haven't found a whole lot of them. Okay, and the reason being is that these objects are hard to find from the Earth just simply because of geometry, the way they go around the sun, and they're also smaller than the 1 kilometer objects. In other words, you need big telescopes. Otherwise, you'll have to find them only when they come close to the Earth. And sometimes they won't come close to the Earth for 20, 30, 40 years. So trying to find all 25,000 of these 140-meter objects within a 15-year time frame is going to be challenging. In fact, of the 25,000 NEOs larger than 140 meters, we've only found about 8,000 of them so far. Okay, very little. We're finding at about 500 objects per year. And at this rate, it would take another 35 years to find all of them. So, which is a long time. Remember, the congressional goal was to find everything in 15 years. Okay, that deadline is this year. So we've only found 8,000 of the 25,000 in 15 years. So this is not a very efficient way of finding these objects. Now, people might argue, why can't we just wait for 35 years? It's an issue of, risk. Can we wait 35 years to find out everything that's out there versus trying to find them before? So what we went and proposed was a space-based telescope called NEO Surveyor. And this telescope is unique in the sense that it doesn't have to worry about weather. Like on the Earth, telescopes are affected by weather. Telescopes are affected by the moon phase. During full moon, like right now, it's hard to find asteroids because the sky is brighter. It also turns out that asteroids are not very bright, invisible light, like the light we see with our naked eye. When you put an eyepiece and your eye to a telescope or your binoculars, or you go in the night sky, the reflected light from sun, from asteroids, is not as good wavelength to find these objects. They seem to be brighter in the infrared, which human beings cannot see. But if you have a space telescope that is far away from the heat of the Earth, it can find asteroids much more efficiently. So that's what scientists at the University of Arizona and at NASA's Jet Propulsion Lab, we all proposed to NASA to find these remaining of these 24,000 objects. So here's a picture of the telescope itself. It's pretty tall. It's about 22 to 23 feet from bottom to the top. It has 2 channels. So in other words, it has 2 cameras. The size of the telescope itself is pretty modest. It's only a 20-inch telescope. A lot of amateur astronomers actually have bigger telescopes than a 20-inch telescope that we're using for this NEO Surveyor. The interesting part is what I told you before. When it comes to asteroids, infrared is the place you want to look for them, not in the visible light like we're doing right now with Catalina Sky Survey, Space Watch, and other ground-based telescopes. They're really good, but when you want to find small asteroids very efficiently, going in the infrared helps a lot. So a 20-inch space-based infrared telescope will find same amount of asteroid as an 8-meter ground-based optical telescope. So you can see clearly the advantage of it. And it's going to a location, it's called the Sun-Earth Lagrange point. So it's farther away from the Earth, but close enough that you can still get data back, but you're not affected by the heat from the Earth. So the telescope can cool itself passively. In other words, there is no cryogen. There is no thermoelectric cooling. Just it radiates heat from all the electronics and everything to space, and it's able to cool itself to minus 390 degrees Fahrenheit. And that's the beauty of this telescope. Unlike other telescopes like Spitzer or the WISE telescope that use some kind of a cryogen, you're not limited by consumables. So you are passively cooling. So the only thing that you're limited by is the life cycle of the hardware that is operating, and of course the scientists who are operating this telescope. But people can be replaced. Here's a schematic of the telescope itself. So you have the solar thermal shield. Obviously, we need to get solar power from the sun, but we can't let it heat up our telescope. And also, it needs to block the sunlight so we can look at the night sky, so to speak. So there's the entrance aperture, the radiator to vent out the heat from the electronics and the telescope. So we got lots of them. And there's spacecraft thermal shields, because there's a telescope, which is the instrument, and there's a spacecraft, which is SC, which is in the bottom. So you don't want the heat from the spacecraft bus to get to the telescope. So you have some thermal shields prevented. And the spacecraft bus is what processes the data and transmits it to the Earth. Like I said, it has a lot of heritage. So we took lessons from the WISE telescope, the Kepler mission, and Spitzer. So it kind of looks somewhere between Spitzer and Kepler, if you look at it. And then we are building the NEO Surveyor telescope. So how will NEO Surveyor do? So far we've looked at it. We found 22,000 near-Earth objects. That's the blue bar that you see there. NEO Surveyor would find about 300,000 of them, of all sizes, including trying to help get to that 90% goal for the 140-meter objects. In terms of main belt asteroids, or MBAs, as they're called here, so far we know about, like I said, little under 1 million main belt asteroids. That's the blue bar in the middle. NEO Surveyor will find about 8 million of them. And of course, comets we found so far in the bottom, 4,000 of them. It will essentially double the number of comets we know. So to summarize, NEO Surveyor will help answer a simple question. Is Earth going to be impacted by an asteroid in the next 100 years? That's what we're going to try and find out. And one of the answers might be that there are no asteroids out there that can harm us. So I think that's an important question that we could answer. It's a small investment to safeguard humanity compared to all the things we do in the world. And I just want to thank you and say what the famous astronomer Carl Sagan said: if the dinosaurs had a space program, they would not be extinct today. So we're better than dinosaurs. I think we can invest a small amount of money to find these asteroids that threaten the Earth. With that, I will thank you for your attention and happy to take some questions.
All right. Well, thank you so much, Professor Reddy. That was an incredible program and very informative. And hopefully folks in the chat have questions for you. I just have a couple of questions, if you don't mind. One would be to just sort of go to the next logical step from the end of your talk there, which is, we get the funding, we find the asteroid, the city destroyer or the continent destroyer, it's coming toward us. What are some mitigation techniques that astronomers have thought of to
Sure.
deflect such a thing?
That's an excellent question. So the best defense against an asteroid is time. So the more lead time we have, the more we can prepare as to what this object is. It's like know thy enemy, right? You want to study this asteroid when it's far away, when we have plenty of time, then we can find out what it's made of, what is the internal structure, what is the damage it's going to cause, and what's the best course of action. So there is an equation where you can figure out, if we have a lot of time, then you only need to gently nudge it so that it misses the Earth. Suppose something is going to hit in a matter of months or weeks or days, the best course of action is civil defense. You evacuate just like you do for a hurricane, and you hope for the best. And of course, it depends on the size of the object. So if it's a small object like the Chelyabinsk size, you would simply make an announcement saying that please don't go near windows. Stay in your bed, cover. You know what I mean? So take the basic precautions. If it's a larger object and if it's going to hit, most likely something is going to impact ocean, because Earth is mostly ocean. And if we have a tsunami, so you tell people to avoid coastal areas. So, there are plenty of options. And of course, we're now working towards another mission called DART, D-A-R-T. It's called Double Asteroid Redirect Test. And this spacecraft is going to go and impact a moon of another asteroid that is a near-Earth asteroid. So it turns out that 1 in 5 near-Earth asteroids are binaries. Just like how Earth has a moon, 1 in 5 asteroids have moons around them. So this DART spacecraft is going to go and hit the moon of a near-Earth object and try and see what happens to its trajectory. So we're trying to find out that. So that's going to happen before we go and launch NEO Surveyor. So we're learning from that as well.
Oh, very interesting. So it does seem like that just the moral of the story is we need more, eyes firmly on the celestial sphere to be able to detect these things so that we can plan accordingly in terms of evacuations and things like that. That's really fascinating. And I just have kind of one more question for you from a more personal question. You're an astronomer. How much did pristine night skies, play in your upbringing or your role in becoming an astronomer? Any experiences you have of, seeing really dark skies that inspired you perhaps to pursue this field?
Sure. Yeah, that's a very good question, because that's exactly what happened when I was a kid. I grew up obviously in rural India, And most of my early childhood, we did not have power. So I grew up without power, especially in the evenings. And there's only so much homework you could do in candlelight and, read books. So I was blessed to have, similar skies as you have in the Grand Canyon when I was growing up. So I had nothing to do. When life gives you lemons, you make lemonade. So I had a lot of dark skies. So I learned astronomy by looking at little star charts that they used to print once a month in the newspaper. And that's how I got interested in astronomy, and I learned myself. And for a long time, I just did astronomy with my eyes. Those were the best tools I had. I didn't have a telescope or any optical device for probably till I was about 18, 19. You know what I mean? So I just did what I could. And then at that point, I bought a telescope, and then I built my own. And I mostly built my own telescope since then by myself or with helps of my friends who are better than I am at doing those things. So that's how I got into astronomy. So, there's a lot, looking at the night sky, it is something very primal to human beings, right? They have almost remained unchanged since, humanity began, and also it gives you a connection. So I've lived all over the world, worked all over the world. The stars are the same no matter where you go. So it literally takes me 2 minutes to orient myself where I am. So I can look at the sky, I can look at the constellation, just like people would get, you go into a grocery run, where to turn left, right. I know this is the same way with the night sky. So I don't feel lost anywhere. So.
Well, that's amazing. Yeah, it is a lifelong relationship with the sky, which I too am growing to understand. And it's amazing to think that started with you at a very young age. So, all you parents out there, if you can get your children underneath pristine night skies, you might have them turn out as stellar a scientist as someone like Professor Reddy here. And hopefully you guys will all be able to do that next year at the 2021 Grand Canyon Star Party, which is from June 5th through the 12th. We hope to be able to have Professor Reddy there next year to be able to interact with you all underneath some of the most pristine night skies in the United States. In the meantime, please stay tuned for the virtual telescope viewing session that's going to premiere right after this program, and ask a lot of questions in that chat room. We hope you have a wonderful time with that, and we hope to see you all next year once again at the 2021 Grand Canyon Star Party, June 5th through the 12th. Professor Reddy, thanks so much for joining us this evening, and we hope to see you next year.
Thank you. I plan to be there.